In this video, really aimed at my MAE 3033 class, but for anyone who's interested, I'm going to talk about using the Multiline function tool inside of Mathcad. And for my 3033 class, I've already given you this document which derives what's going on in here, which is using quadratic-based derivatives, numerical derivative approximations on a set of data to estimate the derivatives, and for a data set using what are called central difference second order derivatives for the bulk of the data, but using a forward difference for the first point and a backwards difference for the last point. And I've already talked about that with all of my students. And so what I'm going to do is jump ahead here and let's take a look at the function that we are using in this class. And I've already given you a printout of this. I just want to show something you ought to do after you have typed this function for yourself. So here is our numerical derivative from array function, where we send in an array of function values. We send in the delta x spacing between the function values, and we tell it the size of the array, and it goes through and loops and does the calculations. I'm going to actually retype this in just a minute to show how to type these kinds of functions, and then maybe a little bit more. But also I want to show testing this numerical derivative approximation function by setting up a range variable that goes from 0 to 36. And I'm going to create an array called signs sub I, which is the sine function going from 0 to 2 pi in 36 steps. I'm going to also create an array called cosines, weird name, okay, which is the cosine function over that same range. Then I'm going to send the sines data with a delta x value of 2 pi over 36, there being 36 points in the array, and I'm going to send that sines data and ask it to calculate the numerical derivatives using the NDA function. And that entire set of numerical derivatives is stored in this dsine array. You've seen me do this before in various Mathcad contexts, where I take two things that ought to be very close to equal, two vectors that are very close to equal, subtract the entire vector, then calculate the magnitude of that vector, which is a Pythagorean type process. And this error turns out to be quite small. And then I plot because the derivative of the sine should equal the cosines. And then I plot the two, but I've added 0.2 to the cosines just to shift the curve upward a little bit to show that they look, in fact, very close to each other. So, how did I create this function? How do you type a function like this? I'm going to type NDA parenthesis F comma delta x comma Imax parenthesis colon equals, and then I'm going to go to the flowchart palette and click on that and bring it into the screen. That looked funny for a little while. Here are the tools that are available on this programming palette, including add line, and I typically add several lines right away before I do anything else, and I can always add more lines or delete lines quite easily. Let's go through what's on the palette. This is the local definition. It's also the program equal key, a weird looking equal sign. If statements, the otherwise is the else. For loops, while loops, breaks, continues, returns, on errors. This is a way to get out of a loop or get out of a function. This is a way to get out of a function or subroutine. On error is a way to deal with or trap certain kinds of errors. We probably won't look at that one today. Okay, but this program is, first of all, just some pure text that I'm using as comments, so I'm not going to type the same text. Hello world. Okay, there's some text on one line and text on another line. And then I'll click in this box. In this box, I'm going to start a for loop. I don't type the word for because I won't get what I need if I type the word for. I'm going to click on the word for here, and it says for something in something, and it also gave me this line which is indented because, and this is the body of the for loop, and right now it's a one-line for loop body. Let me just show you though that if I add lines in this indented area, This is a multi-line for loop. Okay, when does the loop end? There's no next statement. The loop ends when I hit the end of this line. And when I hit the end of this line, I either go back if I'm still looping, or I continue on if I've finished the loop. And just to show you a little bit more, if I wish, I can have nested for loops. I can have a for inside a for. Notice this next level of indentation. This would be a one-line loop unless I add several lines here. And if I wish, I could place an if statement inside this for loop. This if statement says, do this thing if this is true. Now, the thing to do right now is just a one-line thing. But if I add lines, this now says, if this is true, do this thing. And this thing is now multiple lines. And after an if, I could have an otherwise that says, if this is true, do this, do that otherwise. And that's a one-line thing right now. And I can turn it into a multi-line thing. And so my otherwise is now a multi-line thing. And if I wish, inside of this if statement, I could have another if statement, which is multi-line. And inside of this if statement, of course, I can have a for loop, which is multi-line. Okay, and now you see, and this is nothing that you couldn't do in any other programming language, including Visual Basic or whatever. Okay, we have nested programming, leading to the idea of structured programming would be part of it, this nesting. And the indentation lines tell you what is nested inside of what. I can see quite clearly that this if statement is nested inside of that if statement, and that this for loop is nested inside this if, which is nested inside of that if. And this thing is nested 1, 2, 3, 4, 5, 6 things deep. Okay, so that's how you would control sort of overall organization. Now let's actually put it to work on something not as complicated as I've been showing you. Let me shift delete all that stuff. And I will keep my for loop. And let's talk in detail about the for loop. Okay, this says for some variable, I pick it. I'm going to call it I. And then this uses range variable notation. And so I'm going to say 1 semicolon, and I could say 10 or whatever. But in this case, I want to base my loop length on Imax. And I want it to be Imax minus 1 in this case. Because I'm saying I'm going to use the central difference derivative equation on point number 1, which is actually the second point, and I'm going to use it on the next to last point, but I can't use it on the first and last point. And then I will type df dx sub I. I'm just using Mathcad array notation. Now I want to say equals. I can't use a colon equals. I don't use a bold equals. I use the program equal. I don't know why it's not just a colon equals. Seems like it would work, but it doesn't. So df dx sub I, and I'm just going to steal this. I don't want to type all this stuff and take the time to type it. So I'm going to copy that one. And so in my one-line for loop, I've done this line over and over again. Now, the remainder of these lines are outside of the for loop because they're not indented. I can tell that. And so again, rather than, well, I will type the first half and copy and paste. So df dx sub 0 is assigned the value, oops, wrong level, I need a space, is assigned the value, and I'm just going to copy this, copy it, paste it, and I'm just going to copy the entire next line. So looking at the flow of this program, comments, which is just text, they do nothing. A single line for loop. If I wanted to turn this into a multi-line for loop, after the fact, I select here, I've got my insertion pointer to the left. If I say add line, then it adds before. With my insertion pointer, I'm going to hit the insert key to the right, and I say add line, and it adds after. I'm going to hit the delete key because I don't actually want any of those lines. Now, how do we return information from a function, a multi-line function? The very last thing that happens or that is triggered before the end of the program is the return value. So if I say dfdx, which is an entire array, and when it hits this line, I'm not assigning it a value. I'm simply saying its values are the return value. And so when this function returns, these numbers get sent back. An entire array gets sent back. So now what I'm going to do is, now that I've typed this, we're going to see if I typed it right or wrong by taking my earlier version of the function. Since I did a whole lot of copy and paste, this really ought to work, unless I made a typo in what I did type, and it is working fine. So this is your basic, fairly simple, a one-line loop plus a few other functions to be done. Now, just for fun, I want to show you other places where I've used multi-line functions. But the basic idea of a multi-line function is, yes, I probably could have done this in 4 or 5 independent Mathcad statements, okay? But it's kind of nice if I want to use this over and over again in a program to have it all packed into a function with a name that I can call. And so if I wanted to do 10 different numerical derivatives without a function, I'd have to sort of do these 4 or 5 line things in multiple places, and it would take up too much space. So a useful tool with an argument list to customize how it behaves and a set of commands, and this useful tool can be used over and over and over again. And I have already shown you sort of how to click and use most of these things and how to structure the program and do nesting, those kinds of things. Let's see what I have here just for maybe a little more show and tell. Window, Simpson's 1/3 rule program. Okay, when I teach numerical methods or computer methods, I often teach the numerical method using Mathcad as the pseudocode or the sort of non-language language, but this one really works. So most of you are familiar with Simpson's 1/3 rule for doing numerical integration, and this one I'm going to pass in a function, the limits of integration, and the number of values to communicate or to compute. And in this one, I am using a feature in Mathcad that's not available in Visual Basic. I can pass the name of a function to a function and call it within the function. So right here, this thing called f is being treated as if it were a function because I use arguments after it. It's been treating as if it's a function. So when it hits this line, whatever name of the function I pass here, that function will be called here. A very nice feature not available in Visual Basic. As a matter of fact, one of the biggest flaws of Visual Basic for writing numerical methods programs. Okay, but this one has a few comments, a first line, a second line, a loop over all the odd terms, for I goes from 1 to 3 up to n-1, and that's a single line loop. Then a loop over all the even terms, starting with 2, 4, all the way up to n-2, and then finally a one-line thing to wrap it all up, which is multiply by h over 3, and then return that sum. And so just to show how it works, my function f I'm going to declare as e to the x times the cosine of x squared. This is the analytical answer. And let's see, where have I, okay, so let's look at calling okay, so yes, and here's the numerical value of the analytical answer. And here's where I call Simpson's 1/3 rule using, let's see, A to B and N. Using 5 panels to do this. Can't use 5 panels. I would teach that normally in the class. Got to use an even number. But 10 panels, okay. 100 panels, okay. 1,000 panels, and starting to compare awfully good even after after 100 panels, awfully good to the analytical answer. So this would be, I think, a function most of you have seen at some point, the Simpson's 1/3 rule function. Getting a little more, well, let's just go to the Weld stress module. If you take Mechanical Design 2 with me, or actually with any of us, I'm sure, you will learn how to calculate stresses in welds. Well, part of what has to be done is to find the centroid of a series of straight line weld segments. So this is a function that finds the centroid of a series of straight lines recorded by points in the XY arrays. This is the thickness of the weld. And this is an interesting loop, for I goes from 1 to 3 to n. This is only looking at every other point in the set. It is not looping over the even points in the set. And I'm not going to tell you why, but it just makes sense in this one. This is a multi-line loop building up some arrays, and the arrays are finally going to be the x bar, y bar in the area. Then I need to calculate section properties. Moment of inertia about x, moment of inertia about y, the polar moment of inertia. Again, some loops and summing up some things. You might recognize the parallel axis theorem, okay? But it is very handy to be able to call weld section properties given the details of the weld. So it makes tremendous sense, even in Mathcad, to write short programs rather than every time I want to calculate weld section properties, execute these lines using range variables in a fairly large section of code. I can evaluate weld section properties now just with a one-line function call. One thing I will say for my 3033 students, you haven't seen me do this before, I call this a weld stress analysis module. To me, a module in Mathcad is simply a file that can be included inside of another file. Let me show you what I mean by this. File open. Actually didn't plan this, so I'm going to have to go find this file. This includes all of my modules. Let me move up to Shigley homework problems. No, Shigley and text examples. And I think it is chapter, let's see what this looks like. It's taking a little while. Okay, so this is an example 9.7 out of Shigley. I have used something called a reference. I think I will go ahead and teach this to you now. In Mathcad, you can say insert reference, and we can browse. And I will go to classes, 4353, Mathcad modules and examples. I call them my modules. It's my name. It doesn't really matter. And maybe I want to use the clutch and brake module. And it grabs that and it puts it right there. And now all of the functions that I have inside this clutch and brake module are now available to everything down below. It's as if all of this were typed right here. It is also as if all of my weld stress things were typed right here. So I can use them without having to take up very much space. So being able to include another document inside a document and use all those tools is handy. And if I want to see what's inside the clutch and brake module, fine, I double click on it and I see I've got an internal drum brake function with some notes and warnings, and it apparently involves some integrals. And it's one of the longer Mathcad functions that I've written. And it looks like that may be all that I have in there right now. I'm going to go ahead and close this one. Hello. As I said, close that one. And I'm back at the Shigley example 9.7 where I have included the clutch and brake module, which is really irrelevant, so I'm going to delete it. But it does include the weld stress module, so that if I define an array of points, then we saw that weld centroid function earlier. Here's the centroid of this weld group. And at some point we'll calculate, well, here are the weld stresses that occur on that weld. And I'm not going to say anything more about that. Functions and references, inserting references, both very handy.